Hi, this is Pravash. Welcome to Math and More. Today we are going to find out the probability of getting at least 1 6 when we roll 3 dice. We'll not use math, rather determine it experimentally, then verify the answer with math. So how do we do it? So let's try a function called rand because we need to generate random numbers, right? So let's use rand. Rand function generates random number from 0 to 1. So we multiply it by a 6. It gives numbers between 0 to 6 and we round it up, round up to 0 decimal. There you go. So this function gives natural numbers from 1 to 6 randomly, just like your dice. So what I've done, I've used that function to generate 10,000 random numbers, all between 1 to 6. And so I'm doing it thrice for D1, D2, D3. These are your three dices. Um, so what we do is for each iteration or for each occurrence, we see if there is a 6 or not. So this function here, this formula, sees if B2 is a 6, say yes. If C2 is a 6, say yes. If A2 is a 6, say yes. That means if either of these three fields or any of these three fields is a 6, it will say yes. Now it inspects all the 10,000 rows and it will give a yes or a no, right? So now let's refresh F2 enter, F2 enter. It generates random numbers and you can see the values are changing. If you go to this row number 9, it says yes because there is one 6 here. Similarly, row number 11, there are two sixes. It says a yes. So what we do now, we count the number of sixes. This is COUNTIF. So count the number of sixes, count if it's yes. So in this iteration, we have 4,153 yeses. And what's the total number of rows we have? 10,000. So that gives us a percentage of 41.53%, right? So in this experiment or in this iteration, we have 41.53% cases where we have at least one 6. We can change it once we hit enter, F2 enter, it just changes. You can see the number is changing here. Yeah, do it a few more times. So now it's 42.25%, right? We saw it was ranging between 41, 42%. So let's find the same answer using math or using probability. So what is the probability when three dice are rolled that we get at least one 6? So how do we do it? Let's break this question down to something simpler. What is the probability that not a single die will roll a 6? That all the dice will have 1 to 5. That means they'll have 5 out of 6 options. So that will be 5 by 6 into 5 by 6 into 5 by 6. So that gives a percentage of 57.87%, right? So this is a case where not a single die rolls a 6. Now complementary of that would be 1 minus this. So 1 minus 57.87% will be 42.13%. That's the answer. That answer is that's the number of or that's the answer to the question that we have at least one die that rolls a 6, right? Let's try to exhaustively see what are the options we have. Let's go to this tab. If you come here, uh, so we'll exhaust all the options D1, D2, D3. So you may have 1, 1, 1. So with this one, you can in D3 you'll have 1, 2, 3, 4, 5, 6. Similarly, when D2 is 2, you'll again have 1, 2, 3, 4, 5, 6, so on and so forth. So you'll have 6 into 6 into 6, those many combinations, 216 combination, right? So here we have 216 combination. Out of that, I put yes where there is at least one 6. You can see there is a 6 here, there is a 6 here. So the total number of sixes or total number of rows that has a 6 is 91. So this is 91 out of 216, which is 42.13%. So mathematically also it comes to 42.13%. And experimentally we saw the number was pretty close. So what would be the probability distribution? The distribution would be, now if you see, now let's add up the numbers, right? When it's 111, we get 3. When it's 1, 1, 2, we get 4. But you can see 4 we can get from three options: 1, 1, 2, 1, 2, 1, and 2, 1, 1. So that means you have a higher probability of uh, getting a 4 than getting a 3. Similarly, you have a higher probability of getting a 5, so on and so forth. So let's see the probability distribution. This curve shows the number of options where we'll get a certain outcome, right? So 10, we have 27 options or combinations that gives us a 10. Similarly, 11 is also 27, but then I guess again it tapers down. As we go to 17, 18, 18 we only get one option, which is 6, 6, 6. So this is the probability distribution, right? This is the probability distribution. Let's see experimentally how it looks. Let's go to the other tab. So you can see what I've done is I put the natural distribution here, and I put the probability distribution as depicted in the simulation. How am I doing that? I put this sum, which is A1, the A column plus the B column plus the C column. That gives us this value. And what I'm doing is I'm trying to count out of 10,000 the number of times we get a 3, the number of times we get a 4, and so on and so forth, right? So with this, if you can see, this is the simulated value, right? I can just hit enter, F2 enter, because that will refresh the random numbers. You can see the second graph is changing, but it's pretty close to the first graph, which is the ideal graph going by math. So we can see experimentally, as we have a high number of sample size, the statistical distribution is almost same as the mathematical distribution. Thank you so much.